Okay. Yeah, so there's the question of constructing these things quickly. And in this case, in n log n time. And the nice thing about it is actually there's a nice data structure problem that comes up in this this algorithm that has a surprisingly easy solution. Okay, so just a really quick recap about what we were doing last time, at least for the stuff that's relevant for what we have. We had a triangulation, which was a maximal planar graph, so a planar graph with as many edges as possible, which means every face is a triangle, except the outer face, which is the complement of a triangle. And we were looking for this thing that I call a tripod decomposition. So what you do is take any square rectangular faces. So what you do is you take a shortest path tree or shortest path forest to the outer face of your graph. So that could be this, for example. Here's another one. That one. And then let's make it interesting. There. And that's it. Okay. So every vertex remembers or doesn't remember. You make a forest that's rooted at these three vertices on the outer face. If you don't like forests, you can make it into a tree by adding a special vertex that's not really in the graph. And they all belong to one tree. And we wanted to build this thing called the tripod decomposition, which in the big picture, the general picture is you have part of your graph that's contained inside a cycle. The vertices of the cycle have three colors in these intervals, like so. And what you want to do is go deep inside there and find a triangle that if you take the shortest paths from the three vertices of that triangle to this thing on the outer face, that those things cross each of the three colors on the outside. So maybe you get a path like this, and like this. Okay. So this thing here had a name. It's called the sperner triangle. And that's because there's this famous result called Sperner's lemma that says actually it doesn't matter how you color the inside of this this graph, how you color the inside of the colors, you'll always find a triangle. As long as the outer face looks like this, you'll always find a triangle with three different colors. And we actually saw a proof of it, at least a sketch of a proof, and that's worth looking at. So in fact, if you think a little bit about where the colors come from, so the colors of the vertices in here, they are just, for any particular vertex, you just look at the path to the root of this tree, see where it crosses the boundary, and that vertex gets that color. And then, of course, every vertex along that path will get that color because they all share that. I mean, they all share this shortest path. So if you think about what this is going to look like, you'll have some part of your graph which is colored blue, right? So these are all vertices where if I take the shortest path to the boundary, it goes off to the blue section. Another part which is colored purple. And a final part which is colored green. Okay. And the triangle you're looking for has a vertex in each of these parts. And if you think a little bit more about it, I talked about how you might, what the proof looks like for this case. I said what you do is you start at this outer cycle somewhere where you have an edge that's two different colors. And on the other side of that edge is a triangle, which has at least two different colors on it, because one of the edges of that triangle is the edge you're looking at. And then you look at the third color on that triangle, or the third vertex of that triangle. And if it's a different color than the first two, you're done. Otherwise, you walk through the edge that has two different colors. So at each time you walk through an edge that has two different colors. And you can see what's going to happen from this picture. If you start walking here, you'll walk through all these things and then eventually find your sperner triangle. Okay. All right. So there's an algorithm. This proof is very constructive, right? What are the things that you need to do to make this work? So first thing you need to do, so if I give you this as a problem, so the problem that you get is the outer cycle with colored vertices. So the vertices on the outside of this thing, they've got their colors already from some previous step that you've done in the algorithm. You also have the breadth first search tree T. So that's a tree that tells you for each vertex what the next step is on the shortest path to leave this cycle. And well, that's about all you have. So your job is to find the sperner triangle. Okay, so how do you do that? Well, if you're, so a few things you may or may not know. Planar triangulations like this, there's lots of nice data structures for representing them. And in particular, there are things like doubly connected edge lists and even triangle-based representations that make this walking easy. So if you're in one triangle and you want to know get to the triangle on the other side of an edge, that's an easy step to do. You can do that in constant time. Of course, every vertex of your graph belongs to the triangulation, and it also belongs to this tree. So you can think of a vertex as, you know, it stores whatever, the information that it needs about its neighbors in the triangulation, and it also stores something like a list of its children in the tree and its parent in the tree. So if I want to find this sperner triangle, if I want to implement this thing, what I need to do is, well, first find a place on the outer cycle where I have an edge with two different colors. So start anywhere on the outer cycle and walk around until you, this thing. You are given the colors of the vertices on the outer face, and so you just walk around until you find one of these things. That's not a problem. Okay. So you want to find the first edge. And if this thing has size n, then certainly you can do that in O(n) steps, probably less, because probably the length of the outer cycle is smaller than the number of vertices inside, but you never know. That's not always the case. Now you want to walk. I don't know, I call this thing the tunnel. What's the tunnel? That's this thing here. Now, to take a step in the tunnel, that's a step into a triangle like this. I need to know if the step is done, if I found the triangle I'm looking for, or if not, which direction I should leave this triangle. Which means I need to know the color of this third vertex. Now that third vertex is not on the outer face, so it's not already colored. So I need to figure out its color. So there's a few ways I can do that. One is to, before I begin, figure out the colors of everything in here by walking through the tree. Or if I'm lazier, then I can do it on the fly. So I look at the third vertex of this triangle. I don't know its color yet. So it's uncolored, let's say. But I do know its parent in the tree. So from there, I can walk to its parent. And if that's uncolored, then I walk to its parent. And if that's uncolored, I walk to its parent. And then finally, I will get to something that's colored because eventually I'll cross the boundary here. At which case I learn that the color of this vertex is purple. And since I did all this work anyway, I might as well remember that the colors of all these vertices are purple. Okay. And now I know, okay, the next step in this walk should go out this triangle. I need to know the color of this vertex if it's not colored already. Yes?
Sorry, I'm just wondering, would it be possible to do a LCA query with that vertex and the other two vertices to determine its color?
It's not an LCA query exactly, because we like the LCA of this and this could be something out here, right? And that the coloring that we have is for this cycle, doesn't necessarily extend to stuff outside of the cycle. So we can't do that, but there is a data structuring question that is exactly about storing these colorings that we'll have to solve. Yeah, and so I go ahead and do the same thing again. This one has to follow a path until it hits a vertex whose color it knows. Now, the first time you do this, the vertex that you're going to hit is on the boundary, but now when you keep doing this, you might get lucky. For example, for this one, maybe the parent of this one is actually that, in which case you find after one step that this is the color. Okay, so that's how you can do this sort of on the fly. And how long does that take? Well, there's a few things you do. You take steps in the triangles. Well, there's not more than n of those triangles for sure, or 2n minus 4. I mean, a constant times n. You take walks up the tree until you find colored vertices. That you wouldn't necessarily, if you kept doing that and walking right back to the boundary, you might have done more work than you wanted. But the good news here is every time you take a step in this walk up the tree, every vertex that you see, you're going to color, and you'll never have to walk over it again. And so if you count the total number of steps you take in all of the times you're computing the colors that you need to walk through this tunnel, that's not going to be more than the number of vertices, because each time you walk over a vertex, you remember its color, so you'll never walk over it again. So that you can do in O of n time. And then you find the Sperner triangle. In fact, in the act of finding it, you actually well, it doesn't. You actually figured out the colors of the three paths to the boundary from that Sperner triangle. So it should look like this, I guess. And purple and blue. And now you've got this this tripod that you want, this three-legged thing. And remember what we do with that tripod is we are going to recurse on the three parts of this problem, A, B, and C in this picture, except now, right, the picture is going to look like this. There's still the stuff that was colored before on the outer face. And we give the tripod its own new color. So if I look at any one of these problems, I see exactly the same kind of problem again. This one is yellow, blue, and then purple. This one is yellow, purple, and green. And this one is green, blue, and yellow. So three colors on each of the subproblems. And I recurse. Okay. And now the colors that I did here, I can't reuse them anymore, right? Because, for example, in this walk, I colored a lot of things based on these three things, but I can't really reuse those colors anymore. Like, you know, if I'm in here and I follow one of those paths, it might go off to, I don't know, here, for example. Well, actually, yeah, could go off to here, for example. And well, this, if I've colored it already, would be colored blue. So if I'd colored this before I knew what the tripod was going to be, this would be colored blue, but it shouldn't be blue. It should be yellow. So I have to start over with the colorings when I recurse like this. All right. So that's all good. And it seems you can do this dividing step in O of n time. And if you then try and analyze what the running time of this is going to be like, you'd say, well, okay, that gives me 3 subproblems. Let's say they have sizes n1, n2, and n3. Then I'll get a running time recurrence that looks something like T of n is equal to, well, O of n time to find this thing and break up the thing into 3 subproblems, plus T of n1 plus T of n2 plus T of n3, which with the restriction that n1 plus n2 plus n3 is a less than or equal to, I don't know, let's say n minus some constant. All right, that's good. Anybody know what these kinds of things solve to? Yeah, so if you can't tell me anything more about n1, n2, and n3, then you have a problem, because maybe what happens is actually n1 is n minus 1, and these guys are 0. So in which case, then you spent O of n time, and you have a problem of size n minus 1. In the next step, you're going to spend O of n minus 1 time and have a problem of size n minus 2. And if you add all that up, you're going to get quadratic. And this isn't like, you might hope that these things are the roughly the same size, in which case maybe you could get something like n log n, but that's not true all the time. In fact, it's easy to get into a situation that looks like this. So edges of your tree are all going up like this. Your outer face has 3 colors. Okay, so I need to find a tunnel to walk through to look for my Sperner triangle. And so I walk through, well, here's a tunnel right there. It's purple and blue. And so I walk into this triangle and check the color of, did I do this wrong? Yeah, let's point the edges the other way. Like so. I walk into this triangle, check the color that I get. So that means I need to know the color of this thing. It leads me back to blue. So that's an all blue edge. I should walk out the blue purple edge, which is this one. And I'll keep doing that for n steps. And where will I find my triangle that I'm looking for? Not until the very last place that I look, right there. Okay. All right, so that's my Sperner triangle. What are my Sperner paths? Well, there is nothing really happening here. There's nothing coming out of here because it's already on the outside. Nothing coming out of here because it's already outside. So there's really only this path. And in this, so what does that mean that I'm recursing on? Well, that means that I'm going to end up recursing on this problem here. I can forget about this thing, and this path here is going to get a bunch of is going to get a new color, yellow. And now, actually all the way to there. And now in the next step, yes, I'll be able to pick off this first triangle, but the step after that, I'll have to walk all the way again. And I'll have to keep doing this. And this actually happens in a lot of there's a lot of situations where this can come up. Okay. So that algorithm, although it's nice and conceptually simple, it takes quadratic time for some inputs. Now, is there anything you might think of doing to speed it up in practice? Like for examples like this? So this example really is in this tunneling picture, it's somehow really trivial. So here we go. Where's my blue? So, right, the problem is there's a disconnect between this picture, which is ugly, and this sort of nice looking picture, which looks good. What's really happening here is, well, if you redraw this picture, the way it kind of to represent more something like this, what happens is you have this massive blue piece and this tiny purple piece and this tiny green piece. And it looked like this. These are where your edges are. Okay. So you walked down this tunnel to find the thing you were looking for. Is there a better way to get there? Is there a faster way to get there? Like in this picture, I started here. Any reason? No, I could have done the same thing from here, and I could have done the same thing from here. Okay. And okay. Now, if I had done that here, where are the tunnels? Where were the tunnels in this picture? Well, there's a tunnel here, there's a tunnel here, and there's a tunnel here, and the triangle I was looking for was right here. If I'd started at either of the other two locations, I would have found it in one step, not n steps. So that suggests something nice that I can do, which is to start at all three tunnels sort of in parallel, if you like, or that's not really, you don't have to really do it in parallel. You just write a loop that takes a step in each of the three tunnels until the first one finds what it's looking for. And then at least for something like this, you would find it in one step. All right, now that sounds good. So let's look at what happens. So we had T of n is O of n plus T of n1 plus T of n2 plus T of n3. And once we find, right, so what is n1, n2, and n3 here? Well, those are these things like this, right? Here's N1. Here's N2. And here's N3. Now, if I search in all three tunnels at the same time, I'll find it in time proportional to the length of the smallest of those. And actually, if I look at those tunnels, what you'll see is that each one of them is contained in one of these A, B, or C regions. So that means that let's call the tunnels tunnel 1, tunnel 2, and tunnel 3. So what we have is that tunnel I is less than or equal to Ni, the number of things in this region. And I've just said that if you do this tunneling thing, you can do it in a number of steps that's proportional to the smaller of those three things. So this recurrence is going to change now. It's going to become T of n is less than or equal to the min, well, of the tunnel lengths, but each tunnel is smaller than N1, N2, and N3. So the minimum of these three things plus T of N1, 2 plus T of N3. And this is a very different recurrence. So this can never be n squared, no matter what values of N1, N2, and N3 you give me. In fact, the really bad values that you have here, if it's always the case that N1 is just n minus 1 and these two are always 0, then this will be linear time, right? Because this is 0 or a constant, and then this goes down by 1 in each step. So you get a linear time algorithm. In fact, the worst thing that can happen is that you get a perfectly balanced recurrence where each of these things has the same size, in which case you get n log n time. Okay. All right, so that looks like an n log n time algorithm. What's missing? Can I really walk down one of these tunnels in time that's proportional to the length of the tunnel? What? Yeah.
To determine the color, you have to walk all the way back through.
Yeah. So to determine a color of a vertex, I have to take a walk, and that's not so good because that means, for instance, to determine the color of one of these things, this is a tunnel whose length is less than n1, but to figure out the color of that vertex, I end up having to walk over here into this thing, which is not related to n1, it's related to n3. So the time to walk down this tunnel isn't necessarily related to the length of the tunnel. And if things go badly south, then bad news. I get stuck with, I don't get this, I get back up to here again, this O of n. So although I don't take many steps in the tunnel, I end up having to color basically the whole graph. So this is a problem for data structures. Okay. So let's think about what we have here. And this is a problem I thought about for a while, and I knew that there existed efficient solutions. Efficient in the sense that there were optimal, even constant time algorithms for doing what we need to do. But they're hard to understand, complicated, difficult. And then after a while, I realized there's actually quite a simple n log or log n time data structure. that is good enough for our purposes, because we're going to get we're going to end up doing something like n operations and get n log n time anyway. So that's good enough. But let's think about what's happening here. So what we have is this BFS tree. When this outer cycle here gets colored, that means there are some nodes of this tree that are colored. I don't know, something like that. Not that, maybe like that. And yeah, this doesn't matter. Okay, so that's what, you know, the outer cycle here is some nodes of this tree. And everything inside this cycle, well, that's not colored yet, that's also a node in this tree. But what I know is that if I start at something inside this cycle and walk up the tree, I'll hit a colored node. So if I start, so in any of the nodes that I'm interested in, if I start at one of those things and walk up, I'll hit this colored node and know its color. So, and then once I, so that sounds good, right? If so first sort of thing is this query, which is the nearest colored ancestor. So you give me a node in the tree that's not colored, and I want you to quickly tell me what the closest colored ancestor is. That's one thing. Now, after you have found your tripod, what are you going to do? Well, tripod is stuff that's inside this cycle. So that is stuff that's descendants of things in the tree. So you're going to take some of those nodes and color them. In fact, yeah, you'll take, you know, so it looks something like, it'll be one path like this, maybe another path like this, and a third one maybe like this. Because in your graph, this was your sperner triangle. Right. The three vertices of your sperner triangle, you take the paths up and they all get this new color. So that in the next round, when you recurse here, you're going to do the same thing, but now you'll be asking questions. What's the nearest colored ancestor? And the answer, if you ask for something in here, is always going to be yellow, green, or blue. If you ask for something in here, it's always going to be yellow, blue, or purple, and so on. But in terms of this data structure, you don't have to know anything. Okay. So you want to know your nearest colored ancestor, and you want to be able to color a node. So this one takes a node as an argument, and this one takes a node and the color you want to give it. And this thing is uncolored to begin with. You're not allowed to recolor it. It never happens in this algorithm. And so there you go. If you can give me a data structure that does these things quickly, then I should be able to run this algorithm quickly. And in particular, here's what I'll, let's say, ask for. This I would like to run in constant time. And this one I will settle for O of log n amortized time. Why those two bounds? Constant time here, because it does happen during the course of this algorithm that you ask the same question of a node more than once. So it can certainly happen that while you are recursing on A, you encounter a node that you had also saw when you were recursing on this whole problem. We know that in total, though, if you add all that up, because you only see those nodes when you're doing these walks, it's not going to be more than n log n of these kinds of queries. But and there could be really as many as n log n. But these coloring operations, each node gets colored when it joins a tripod, and then it never leaves or never gets recolored. So there's only going to be n of those. So if these take O of log n time each, then that's still only going to add up to n log n. So how do we solve this problem? Sounds hard. These are pretty tight looking requirements. Well, so we should then, if you don't know what to do, then you do something you've seen before. And something we've seen before was this so-called Euler tour technique. So this is where you walk around the tree like this, revisiting nodes as many times as they have incident edges. Right. And if you do that, then you get a long list of the nodes in your tree with repetitions in it. Okay. And each node gets an interval, which is the first time in that it appears in that sequence, and then the last time that it appears in that sequence. Okay. So you get these intervals, right? If this is the node X, and these are nodes Y and Z, then you'll find that the interval for X looks like this. The interval for Y starts immediately after X's interval starts, and then goes to somewhere there, and then immediately is Z's interval starts. Yeah, and so on. So you get some representation of the same tree, but now the nodes are represented by these intervals. If one is an ancestor of the other, then its interval contains it. And how many endpoints of these intervals are there? Well, that's just the length of this walk here. So each time you take a step in the walk, that advances this thing by one. There's n minus 1 edges in the tree, and you cross each edge twice, so that's going to be something like 2n minus 1 endpoints of intervals. Okay. And actually, if you use 2n minus 1, then nobody has to, no endpoints have to share the same location. Everybody gets their own endpoint. Okay, that's good. So two n minus 1 is not big. Sounds like something you could put into an array. And what does it mean to color a node? Well, that is just a node has an interval. So what you want, so when I color a node, what I would like then is each of its children should get that color. And in particular, the way in which I color things, well, what you'll find is the root always gets a color and then some children of the root. But in particular, I never color anything which has a child which has already been colored. If you think about that for a little while. So, so that means over here, when I color something, that would be just coloring an interval here. Right? So this is the node X. Maybe this is the interval for X. I could just say, okay, store the color blue in all these array locations. So that sounds, well, it sounds like it's going to be slow somehow, right? Because some of these intervals are very big, so coloring them is not going to take log n time. It's going to take linear time for, let's say, for this one, its interval goes right from the beginning to the end. But maybe in some, maybe if you add up all the costs of those things, it's only going to be something nice like n log n. So maybe it's log n amortized time. But if you think about that for a bit, that's not going to work so well either. Because you can have a tree like this. Its intervals look like this. So if I ask you to color this node, then that's this interval. So you have to color the whole array. And if I ask you to color this node next, which can happen, that's this thing. So now you have to recolor everything except two values in the array. And then the next one is going to require everything except four values and so on. So that looks quadratic. Any idea what to do? So this actually feels a bit like the problem we were having before. Like this thing is colored blue. And then I ask you to color this thing, which is colored yellow, and it's a really long thing, and it recolors all of this blue. Now somehow the difference between those two colorings is not so big. Yes, a whole bunch of colors changed here, but what there is there's two colors. One of them occurs a couple here and only two places, and this one occurs in a whole bunch of places. Before I colored this one yellow, the blue one of the colors occurred everywhere. So it kind of sounds like it would make more sense when I say to color this yellow, then what I should maybe do is somehow imagine that I'm going to leave it blue or leave it the same color and just change the colors of these two things. And actually, if you look at the operations that we end up doing with these intervals, you're always coloring something that has no colored children, may have a colored ancestor. So it really is always the case that you have an interval of colors and you want to change some subinterval of it. Sometimes it's faster to really change everything in that subinterval if it's a short subinterval, but sometimes it's faster to change everything outside that subinterval. So how do you implement all this? Well, first thing you do, you don't store colors in the array. So this is, the moral here is, little tricks that we've seen throughout this course. So use indirection. So don't store the color blue everywhere here. Instead, everybody stores a pointer to one thing that says blue. Now, someone comes along and says, okay, I need you to color this interval yellow. So in this case, so I really do want this interval to be colored yellow. So, so how do I do that? Let's say that this yellow interval really is almost the entire blue interval. Yeah. Take these two things. I don't want to mess around too much, so I will split. Blue, blue, yellow. Okay. So the time it takes me to do one of these operations is proportional to the smaller of two things: the stuff whose color is changing or the stuff whose color is staying the same. Okay. And you can still answer queries in constant time, right? You just still go straight to the array location for the, let's say, the starting point of the, well, each of these guys has a left endpoint of its interval. If you look at the color that's there, that'll tell you the color of the nearest marked ancestor. So now you just have to follow a pointer instead of reading the color directly, but that's not bad. But the claim now is that if I do n of these operations, like in this tree here, so never recoloring a node that was previously colored, and never coloring a parent of a colored node or an ancestor of a colored node, that this all runs in n log n time. Does anybody give me a reason why? So there's still like a lot of pointer changing happening. Anybody? Let's focus on just one thing in this array. So all the work here, I mean, each operation has to allocate a couple of these things, change the values maybe in another one, but that's all constant time. The hard part is changing a bunch of pointers here. So what we really need to count is how many pointers we change in total. And one way to do that is just to look at one of these things and count how many times the pointer at this one could change. So, what's that? Only because it has size exactly 2 in this example, but if it had size 3, it could change again. All right, so, so, so let's think about it. Focus on just one of these locations. Now, when we start, nothing is colored, or if you like, there is one interval whose color is white. So this guy, when he starts, he belongs to a white interval, and the length of that interval is 2n minus 3. Now, at some point, for the first time, I have to update this thing's pointer to point somewhere. What can you tell me about the interval that it's contained in? After that happens? Yeah. So, so initially it was in an interval of length 2n minus 3. Maybe some cheap recoloring happened in the meantime. So maybe that interval got even shorter without having to change this pointer. For instance, you kept coloring like this, then his pointer doesn't have to change. So at this point, at the first time his pointer changes, his interval is not more than 2n minus 3. So it's some value L less than or equal to 2n minus 3. But now we're going to change him. And that's because it was cheaper to change whatever the k things that are in this interval that we're recoloring now than it was to change the L things or L minus k things and the other side. Okay, so what we have is something like k is less than or equal to L minus k, which is like, what do we have? Yeah, L is less than or equal to 2k, k is less than or equal to L over 2. So now he's left the interval of length L and joined an interval of length k, which is less than L over 2. And L over 2 is less than, L is less than the interval he started out in. It may have gotten a bit smaller, so that's going to be 2n minus 3 over 2. So the point is, his interval he got his pointer changed, means his interval was recolored, and now the new interval that it's stored in is less than 1/2 the length of the previous interval that it was stored in. Well, that means that this thing can only be recolored log base 2 of 2n minus 3 times before it's stuck in an interval of length 1. And that can happen, for instance, when that thing happens to correspond to a leaf of this tree, and you somehow color everything along the path. So that's the number of pointer changes that happens here. It's at most log base 2 of 2n minus 3, but there's nothing special about this. That's true of every array location here. So if you add up the total number of pointer changes in all the array locations, it's not more than 2n minus 3 times this. So it's O of n log n. So really simple structure. A good example of sometimes overthinking a data structure problem too much, because before this, before I noticed this, I was looking at the old literature and some very complicated things, but turns out it's easy. If you care about these things, then actually it turns out that you can do even both of these operations in constant amortized time per operation, but that requires something considerably more sophisticated than just an array with some pointers. In particular, it requires those tricks like we use for lowest common ancestors, which is lookup tables that store all the possible subproblems of a certain size, the so-called micro-tree approach. Okay, so that's a good place to stop. I don't mind ending early on the last day. Thanks for taking the course. What's left? So I guess each of you owes me, except for one of you, owes me a project. And if you haven't already pointed me to your contribution to public knowledge, do so. Those things are all due. Does anybody know if there's classes on Monday? Well, let's say they're all due on the 23rd of December. I won't let you work on this stuff over Christmas and ruin your holidays. Feel free to submit them sooner if you don't want to be stuck working.
Sorry, some of us actually have sent you emails regarding the public contribution, but we haven't heard back yet.
Yeah, I've got a few of those things to look at, but I have received those, and I'll basically evaluate them as I go. But what I'd like to avoid is too many emails of the form. Here's my contribution. Is it good enough, or is it a high graded contribution? Once you've told me what your topic is and I know what it is, then go ahead and do it, and then let me know when the final version is ready. Yeah. So, but I will look through all those quickly to see if there's any sort of outstanding questions in terms of whether this is completely in the wrong direction or not.
Pat, I have a last question. Will there any adjustment be made to assignment 1 grades at all?
So I'll be taking, so we've not done assignment 3. So I'll be replacing the grade of assignment 3 with the best of your 2 grades from assignment 1 and assignment 2. Now, assignment 2 is considerably shorter and I think easier than assignment 1. So hopefully that works in your favor. But otherwise, I don't want to do too much playing around with the grades. I mean, this is a grad course after all. But I mean, what I would like you not to do is focus just on your mark in this course. I don't think anybody is going to get a terrible surprise when they receive their marks. So that's what I can say about that.
Okay, thank you.
Okay. All right. So go home or go have a beer with each other or something. Yeah, celebrate the end of this interesting semester. Yeah.
Professor? Pat, sorry.
Wikipedia username. That's
Yeah. Yeah. If you just tell me your, just point me to the article, tell me your Wikipedia username, I can go over it. And that way, if things, even if things have changed since you made your contribution, I'll look through the history and see what. Yeah. It's basically as late as I can get away with submitting the final grades. Yeah, without getting in too much trouble.
Pat,
Yes.
so we won't be expecting getting our grades for the assignment too, like in this week.
Yeah, I'll be sending back the assignments graded as soon as I get there. So you'll get something back.
Okay, thank you.
Okay. All right. See you, hopefully, some of you in the new year in person.
All right. Thank you, Pat. Have a nice holidays.
Take care.